In this video, we're going to explore some of the principles of amplitude modulation as explored in a laboratory that we often do in EC 3084 Signals and Systems, or you could call it Systems and Signals, at Georgia Tech. To begin this demo, let's listen to a few strains of a local Atlanta band called the Extraordinary Contraptions performing Prelude to the Nocturnis. So we are listening to both my voice and now the music out of the JBL. Sorry, I don't have any fancy mixing here. Through the microphone, camera, microphone and the camera.
Gather round now, my young sailors.
Over here on the right, you can also see the music that you're listening to on the oscilloscope. So this is a time domain representation of the signal. I can change the volts per, or the time division to zoom in on the details. I can also change the scale per volts in order to be able to not have it too high one direction or too low the other direction and take a look at it. So if I stop the scope, I can also move over to the dynamic spectrum analyzer and look at what this song looks like in the frequency domain. So most of it is living down here, below 500 hertz. There's a lot of details. There are details up here, for instance, cymbal hits will be happening, hi-hats in this higher frequency range. And really there's detail on a lot of the instruments that's up here that you may not be seeing on the scale. You can see that a little more detail if I put it on a decibel scale, but I found for our purposes for this lab, it's actually best to see these things on a linear scale. I've also put the averaging mode, which is usually set to something like RMS. I think when you, by default, I've set this averaging mode to none. This frequency span I've set to 40 kilohertz, so this can reasonably represent a fairly large range over the course of doing the following experiments. If I simply just wanted to look at audio signals, I would probably, whoops, that's 2000. I would probably set this to 20,000, but it will be useful in a bit to actually have this at 40,000. We'll leave it there. And at this point, I will confess to you that I have somewhat enhanced the truth. Although we have been looking at the original Prelude to the Nocturnis signal, what we've been listening to has actually gone through a modulation and a demodulation process, a double sideband amplitude modulation process with the carrier at 20 kilohertz. To see how this works in more detail, I'm going to switch both what we're listening to and what we're watching using the oscilloscope to the output of the modulator. So our modulator and our demodulation stage are both being performed by AD633 integrated circuits from Analog Devices. They're high precision modulation circuits. And the one on the top here, which we call ICA, that's the modulator. The one down at the bottom here, ICB, that is the demodulator. And right now, let's listen to it, the output of now, and also look at, we'll start looking at the, with the spectrum analyzer here, the output of the modulation process. So we're both going to listen to it and look at it. Now, you're not actually seeing, hearing. You're not actually hearing very much. I'm not even sure camera, especially mic, especially after YouTube compression, will pick this up, but there's kind of this very tinny kind of sound. That is the modulated signal. That is what, in fact, we were using to then demodulate and get the music you're listening to just a bit ago. But it's all at an extremely high frequency. So right now we're looking at the actual input to the modulation process. Let me switch this to look at the analog input 1, which is set to the output of the modulator. So we see what happens here is the frequencies that started at much closer to DC have now been shifted to live up here at 20 kilohertz, according to what you get if you multiply a signal by a sinusoid of some frequency. I can look at the effects here. If I take this 20 kilohertz and start shrinking it, you'll see two effects. You'll see this move to the left, and you also start to hear a little bit more of a distorted version of the signal. I'm going to restart the song. So down here, this is around, let me put it exactly at 440 hertz. So you will find out later you won't be able to reconstruct the original signal from a carrier this low. So dropping down further.
You see a strange shadow beneath the surface. Tell the helms
down at this point, this is 1.5 hertz. You can actually hear a pulsing of the amplitude modulation.
It's the summary of the Nocturnis.
Around here, that's basically the effect of the Daleks in Doctor Who. Their voices made by a similar technique. Let's crank that back up to 20 kilohertz. So now we see the information content of the signal appear at 20 kilohertz. A real quote-unquote AM modulation scheme that's trying to go over the airwaves is going to operate at 100 kilohertz or higher. So it's in the 100 to 1000 sort of kilohertz range. And that's associated with what you're used to on your FM dial. So 850 FM would be 850 kilohertz modulation. Now, the scheme used in commercial AM broadcasts is slightly different than this double sideband scheme I'm describing here. We can talk about that a little later. Before I continue, I want to mention that this is at the amplitude of my modulating sinusoid coming out of the function generator, as opposed to the actual signal we're modulating that's coming out of my laptop. That's what the music is playing off of YouTube. This I put all the way up to 10 volts peak to peak. So if I turn that down, if it's not nearly as loud as you want it, maybe you forgot to set this higher. So for this lab, we're going to set this up all the way up at 10 peak to peak. So there we are back at 20 kilohertz. And again, that was actually what we were listening to earlier, but through a demodulation process. So we're going to take this signal, run it through the second integrated circuit here, the we're calling it ICB, and all it does is it's another modulator. It essentially takes the modulated signal here, multiplies it by another cosine of the same frequency, and in fact it's the same cosine coming out of here. So let me switch both what we're listening to and what we're looking at to the output now of that second multiplication stage, the demodulator. So I'm going to stick that down here. So pretty good. Let me restart the song again. And now what I'm going to do is let's listen to the output of the demodulator as I lower the frequency. So here's 25 hertz.
Tell the helms when to steer clear. There's a craft near the Nautilus that travels beneath the same waves.
So at lower frequencies, you could make out the music, but there's a lot of extra crud in the signal. There's a couple things going wrong there. So at such a small frequency, the problem is if you look at the spectrum of the original signal, so we're still listening to output, but looking at the original signal, it covers a certain range. So you need to pick a carrier frequency so that when you go through the modulation process and then run it through a second multiplication of the cosine to demodulate it, that when these copies shift back to the middle, they don't overlay on top of each other. So you need to pick a sufficiently high carrier to be able to get the original information back, which is why a carrier this low is going to have problems. There's information that's smearing on top of each other in that process. So let's put it back up here for a second and talk about a few other odd things that are going on here. So for again details of that, I'm going to switch back to both listening to and looking at the input signal. No, sorry, the output of the modulator. So here's the output of the modulator. Oh, let's look at it. So again, here I've put it around 11 kilohertz and up and down. Let's see what this actually looks like now. This craziness on the oscilloscope. So unfortunately, I can't run both of these instruments at once. You have to stop one and then start the other. So if I run this guy, what I've played with here is let's put this on 100. Change the scale for division. There we go. So the green line is the original music. The blue line is the result of that first modulation. So you can see that the output of the modulator overall, its envelope overall follows the original signal. And that's a little more obvious the higher this goes. So let me push this back up on 20. I'm going to restart again. See, let me put it somewhere in the middle there. So at these higher frequencies, you can really see the waveform. Here's the green, that's the original signal. The blue waveform sort of fills in the green on the scope. And those are the very dense sinusoidal patterns that come out of that multiplication process up here. As I lower this cutoff, and remember in the frequency domain, we saw the spectrum move to the left on the spectrum analyzer. Here you'll see this blue filled in, becoming a little more sparse as I decrease the frequency. So let's go back and look at the spectrum analyzer and talk a little bit. Well, actually, no, let's do it here. What I'm going to do is I'm going to leave the oscilloscope up for a second. I'm going to take my outputs, and from these outputs, I'm going to so I'm going to listen to and look at now the output of the demodulator. First thing before I actually look at this assignment, notice in what we're just looking at the output of the modulator, the original source I had on a 200 millivolt scale, and then the second source, this is the output of the modulator, I had it on a 100 millivolt scale. And so I had it 200 here and 100 here, a difference by a factor of 2, because going through the AM modulation process, when you look at the Fourier transform properties associated with that, basically the signal gets divided in half. There's a 1/2 that shows up from the math. And so by putting the scale down to 100 instead of 200, I was able to sort of plot those both evenly, sort of on the quote-unquote same scale. Now the demodulator, that introduces another factor of half. So now we're down by 1/4. So what I'm going to do is turn that even down to 50 to be able to put these things on the same scale. So So this is effectively multiplying it by 4 relative to the original input. So same game here. So this sounds pretty good. But if you notice, there's something very weird about the plot. If this was really the output and the input matching, you would expect to see both traces being the same. And instead you see this very, very dense blue matter, basically, on the scope, filling in that green plot. So the green's the original, the blue's the output. Yet, that would indicate there's some high frequency information in here, and that's true. But let's see why this still sounds so good. Let me first actually crank this down when we know it's going to give some distortion just for fun, and watch this anyway.
It might be the cloud going ahead, supplying power.
So here you can see the blue filling it in, but it's not quite as dense.
For the Nocturnis
Going back out. So, to get a handle on this, let's go back to the frequency analyzer. And now we can see why I wanted to put this up at 40 kilohertz instead of down at 20 kilohertz, which would really all we would need for most human audible audio. So let me restart that again. Oh wait, need to stop the scope, need to start the spectrum analyzer. So now this is the, let's see, I put this on I1, so this is the original signal going in to the modulator, so this is the pure signal. But what we're listening to is actually this. So we're hearing this. There is another copy up at 40 kilohertz. Remember, the modulation process took this from 0 to 20 kilohertz, and then the demodulation process, the way it's implemented here, it's basically just multiplying by another cosine. So when that happens, the copy at 20 kilohertz comes back down to DC, which is what we're listening to. But then another copy winds up at 40 kilohertz. So this is actually a slightly sloppy implementation. To really finish the process of getting the original signal, you would want to put a low-pass filter here to kill off this high-frequency copy that's hanging up there at 40 kilohertz. We didn't really bother with that here because of two reasons. One is, you as a human cannot hear the frequencies up here. And also, these speakers are not designed to be able to replicate sound up to 40 kilohertz. Same thing with headphones. So both the playback mechanism can't handle frequencies that high, and your ears couldn't pick them up anyway, even if we had speakers capable of doing that. So the next game I want to play is, let's lower this, and for the Extraordinary Contraptions, let's figure out how far down we can go in the carrier frequency before it feels like, before it sounds like something's wrong.
If you're in the wrong place, the wrong time. Well, the crowd is insane when he has one goal.
Definitely there. There you can hear an artifact. There's a little bit there. You may not be able to hear it on the camera. So here's 7.8. That's not bad. Here we are back at 20. Now, an important point to make is, this is a place where not having that filter cut off, or not having that low-pass filter, becomes important, because it's not necessarily the case that we're having information smearing on top of each other because the carrier is too low. We may just be in a region where here, that extra high frequency copy becomes audible. And I think that's actually what's going on here. So let me crank this down a little bit. We're definitely in a region where you could hear this high frequency copy. As I start to drop this down, what you'll see is there's a place where not only there's this high frequency copy that normally would want to filter out, but this is going to land on top of the original spectrum, and that's the place where it's really going to sound like a mess. So there you're getting some very distinct distortion, just beyond hearing the original song, but just with some high frequency crud in it. Because down in this range, that's where even in the original modulation process, you're losing information. There's information falling on top of each other. Let me crank that back up for the last note. I kind of like that, that's fun. So, there's an illustration of double sideband amplitude modulation. An actual AM radio station and receiver setup uses a variation of this technique. One reason we're able to do this double sideband trick here is that we had the same carrier for both the modulator and the demodulator. For this technique to work, it's extraordinarily important that the frequencies and the phase match. In particular, the phase. If the phase between your modulator and your demodulator isn't locked, then you get situations where you don't get as much volume out. And in fact, if they're 90 degrees apart, when the different copies of the spectrum fall on top of each other, they can actually cancel each other out and you don't get anything out. And to be able to figure all that out requires much more modern, usually digitally based techniques of various sorts. And we're talking about technology that had to work in the 1930s using relatively inexpensive, not terribly complicated equipment. So the basic method is that a real AM radio station basically sends a copy of its carrier along with it. So there's the spectrum like what we saw earlier, but there'd also be a very big spike of a 20 kilohertz signal, or in the case of a real radio station, it would be 500 kilohertz or whatever. And the demodulation scheme for that is very different. There, what you do is of course, with all of this, you filter out frequencies that you don't need, and then you actually do a nonlinear operation. You take its absolute value, that's referred to as a rectification step, and then you filter that. So that might make another interesting lab that's a bit more difficult to mathematically analyze. There's other sort of schemes. There's single sideband modulation, which isn't used for commercial broadcast radio, but is popular among amateur radio, ham radio operators. So with that, I'll bid you adieu.